14.
Already, but it wasn't full time.
For 20
Oh, yeah. If it were full time.
Yeah, I mean, it does pick up
Yeah.
pretty well, so, and I can certainly send out the.
But no, I'm not gonna work 20 hours a week, but I'm gonna rent.
Yeah, it looks, I think this makes.
Yeah.
MGH, under imaging lab,
That's so fun,
No,
but
because
not really.
but not.
I mean, my parents pay for my home right now, which is great.
You want me to say anything?
But,
Like, I don't.
Feel free to say
I
it.
live this year.
Okay,
And
I mean, I can
like
feel
if I
like
was
any
only working
questions
40,
that I know
like,
the
I
answers
could
to.
Yeah, cause I like 100% intending to use college to pay rent,
yeah,
and no,
I use my college pay for
yeah.
Yeah.
But then it's like, I don't know, I think it cut to like.
Wow, you pay them, wow.
I mean, it's
We just
fine.
have to.
Yeah,
that's
that's true.
Yeah. Yeah, I mean, I don't really see the point of like.
Next one.
Not really gonna have that much chance of choosing.
Until she sends me the coding challenge, I probably should just do it as practice.
Instead of back.
And send it back, and she'll be like, wow, you're amazing, you want to do the job, and I'll be like, no, sorry. She was so nice, it was sad. I was like sitting here like, oh, you seem like you're really enjoying this and want me to work here, and I'm like, guess I'll just keep going through this interview. Well, I absolutely know I can't keep the position because it doesn't pay enough.
Just don't do the coding challenge and just whenever she sends it, just ignore back saying I can't accept this job because
It won't cover my rent.
yeah.
Or now or after, whenever.
A small stipend.
Okay, yeah, that goes for the same with all of you. Feel free to grab pizza now. Obviously, it came earlier than usual. And it came way earlier than last week with the show at all.
Are those all the same?
Yeah, so the one on the left is, or my right, is the vegan pizza.
Oh, it's in a full-size box.
It is, yeah, which is a little weird.
It's always the small box.
But, and obviously there's 5 boxes and there's only 10 people here, so it's, feel free to grab one.
Hey, there are still 5 minutes until math club really
Whatever
starts.
happened to the pizza from last week?
It didn't exist.
It didn't end up getting
We
ordered.
went for my
Oh,
midterm.
nice.
We went for my Ringfield midterm one.
It was really a combination of, yeah.
Pizza.
Now? Yeah, already? I mean, there's only gonna be like 15 people here, like, it's not gonna be chaotic,
Okay.
so. Feel free to spread out though if you want. Up to you.
One of these days, we should get pepperoni.
See, yeah, I mean, every single week it's like, do I get something other than cheese? And then it's like.
But there are so many pizzas. They'll get eaten.
Right, exactly.
Anyone who actually likes it.
People will eat pepperoni, I feel. Who wouldn't eat pepperoni, right?
So like,
Don't like it, we have to.
I mean, I would know the pizza that I would, so like, I would always be able to bring it back to my room.
So the.
I'm not like-
I mean, obviously.
It was structured very similar to-
There's already like.
No, I do that.
About the knot theory thing. I thought of something that I thought of a goal that I wanted to figure out how I want to work for knot theory. So have you seen the number? Have you seen how many ways have you seen someone tie your shoes?
Sort of show that.
Oh, yeah.
Everyone tells me that,
Backwards?
I don't know what that is.
I don't know what that means either.
But every time I do it, they're like, Sarah, just
Show that.
like the knot looks backwards.
What?
I don't understand.
Do you do? So I've seen, you know, the standard 2 bunny ear method.
Or the other one
And
where you pull them simultaneously through this, yeah.
Huh?
Or the other one where you pull simultaneously after acting through.
Just whatever it
is that,
He also like.
do you like the one like this?
Yeah, that one also exists.
Yeah, that's the one that I do. And that one's probably my favorite, that's
I
my
was
favorite
starting to
one.
go opposite. Apparently it's backwards.
Yeah,
Yeah, it's backwards.
backwards.
It's backwards. I don't know how I tie my shoes. I can't tie it the other way, like.
It's
it's
backwards.
Oh,
like
yeah.
So it's like your templates will feel like, well.
Oh, God.
I don't know.
I
It was like,
don't.
it was like my second year.
I don't know
Oh,
why.
yeah,
I
shoes
do it that way.
That was so.
That's how I learned to tie my shoes. I can't.
Hey, but
tie
wait,
my
what method do you use to tie your shoes though?
I asked a question on the piazza. I was like, oh, that is, if you responded within
Ready?
8 minutes, I was like,
Like
damn.
one move,
Could be.
go
Ready?
around.
Yeah, one
Less
loop,
devotion.
go
I
around.
respect it.
Oh,
Yeah, but one, so there's one bunny ear
I
method.
had it for Providence.
But it's
House.
not.
It was a very-
it's.
I won.
All right.
Go through, no. Okay, no, start again.
Now, yeah, here, do it.
No, that's like, I think.
Look, it's not
I've
backwards.
like said my opinion too, like it's
Yeah.
counter with that or something like that, I don't know.
Oh,
It's
but
like
it's-
that's-
well, okay.
I feel like
Yeah,
stacking like really complicated. It's not like guessing through already see
I don't know.
whatever problem.
And then
It's like,
Oh, yeah.
even if we know this, and then just assume.
I think this way is like, I think that way is the most uncommon way though.
Oh, yeah.
Sure,
I felt the
yeah.
opposite.
Like,
I felt like stats.
I have never seen another person, like another person until now, to you, like, know that method.
We'll just use the formulas.
So tell you what, we have like 2 meetings where we don't have anything scheduled. It's like, we could just spend the entire time talking about how people tie shoes.
Actually, I found some other, I found like another, I found like so I was looking at like earlier this week on like the top 100, the biggest 100, the top 100 papers by most citations, which I don't know why they chose most citations over age index, I don't know, but one of the papers, most of them are bio papers, but some out of the math papers, there was this one paper called it's just called fuzzy sets.
Yeah.
And it's about this whole thing, called like fuzzy math or like fuzzy logic. And I'm reading, I was looking at the paper, and because it's so like, I guess like fundamental, it's just like, you know, like it's just like something about sets. Like I can actually read it, and it's like kind of interesting so far. And then I was thinking like at one point we could do like student talks, maybe that'd be cool.
Yeah.
Although the quality of student talks, of course, like you know, given that the quality of student talks will be, once everyone's okay with like, if everyone's okay with the quality of student talks being like lower. It's fine.
Well,
That's the best way to learn anything, is to give bad talks.
Yeah.
That's true.
I think it took me like 5 talks before I eventually gave my first.
Only
okay
5?
talk.
It took you only 5?
I don't think I ever gave a good learning. You know, like the ones where like, you know, your job's on the line, yeah, just like up and then you go to grad school, it's like, learn about this.
The ones where like
And I learned so much math.
the ones where like the Eminem song is playing in your head. It's like, one community, bomb spaghetti.
Yeah.
Like, you're the ones that always work out.
Have you done the midterm yet? I did do the midterm. I did the midterm today. But yesterday I was like, I need to do something. That's not school.
Sorry, does that work out?
Doing one?
It doesn't feel
So-
like spring break.
Okay, hi everyone. So if you arrived late, 2 things, please scan the QR code, attendance form and all that. Also, feel free to get pizza. There's 1 box of vegan, which I think has been buried underneath boxes of cheese, but it's in there, I promise. But the rest is just cheese pizza. I really have nothing for you. Obviously, we are not meeting next week because it's spring break. There's a few of us who potentially may be going down to the math symposium at Brown next Saturday. If you don't know what I'm talking about, check your Discord announcements. And it's probably gonna be about 5 or 6 of us. The department would be covering like train tickets and stuff. So yeah, so like it would just, you know, it's free, come down, have a good time. So that's about it. Reading groups have started. So if you wanted to be in a reading group and you weren't, or if you are in a reading group and have no idea what I'm talking about, again, check your Discord messages.
Or if you're in the group theory reading group and really want to give a recommendation because no one has on texts, so I don't have to choose it alone.
You're right.
That'd be great.
And so today's going to be a little bit different than usual. Not so much a speaker presentation, but more talking about the REU that's being offered this year. Just real quick, can someone online say if they can hear us? I guess Joseph?
Yeah, I can hear you.
Fantastic.
Here you go.
Yeah. Cool. So yeah, so that's all I have. I'll stop talking now and pass it on.
Thanks for having me. I'm Josh. I'm on this list here. I'm one of the co-organizers of this year's summer REU here at Northeastern. The application deadline is next week, so it's my last chance to give a pitch. So today's the pitch, and it's cool to see that there's like that you guys actually do a lot of stuff. Like my math club in undergrad, we basically ran a shop. We were in the 10th floor of like this building. There's like no food around, so they just ran a little shop in this closet that sold like Costco muffins. And I think every semester we had like dinner with faculty. So yes, you all are doing way more than what I had back in the day. That's really cool.
That's pretty cool though.
Yeah, you should sell Costco.
Yeah, it's cheap.
Yeah. a lot of little rent. You get that safe, the safe,
Oh, yeah.
and they call.
The math on copy.
Yeah, that could be your shot. Okay, so anyway, so I want to talk about this math REU. Math research is a really big thing, so maybe a little concrete. And then talk a little bit about the projects we are considering. Some of them have been approved, and then hopefully I want at least the last 20 minutes to just have Q&A. Mache is another organizer. He organized it last year, so he has probably more accurate things to say than I do. And Nick was a member. Okay, so basic info. About 2-month program. This is like the summer 1 term. 28th. People are talking about, oh, your money problems. Okay, so $2,000 monthly stipend. It's nice, you get paid. And yeah, you just work together in small groups on a research project. Each group is, the research project gets proposed and also supervised by a grad student. So the projects I'll mention at the second half of the talk. These are all proposed by grad students. They'll be kind of through it. Some of them we've approved right now, others we're still considering. And the workload should be like a part-time job. Well, again, your supervisor graduate students, so what composes those 20 hours. Well, it might be different week to week, and then also depending on what your grad students is. We set things up to be remote this summer. Oh, that's also one of our grad mentors this summer. So yes, yeah. Oh, no, I think. Yeah, so it'll be remote. Of course, again, everything is with your team. So if you want to meet in person. And then again, the deadline's due next week. So that's just basic info. Okay. So getting paid $2,000 a month, what are you doing? Doing math research. What does that even mean? Do research. Who knows? Okay, so here's my really biased view of what math research is. I'm a very problem-centered person. I see a nice road, I go look for the potholes. I don't care about going in those potholes. So yeah, here's my basic view on math research, kind of in 3 steps here. Okay, so first, you gotta find and understand some problems to solve. Okay, there's the pothole. And what does that really mean? Really, right, you gotta learn some background material. Right? See how other people handle things. There's probably a lot of definitions I don't even know yet. Gotta learn background material. Once you get a lay of the land, try to come up with a plan. And this is probably the vaguest part, right? Coming up with a plan. Sometimes a lot of that involves computing a lot, code, either by hand or by computer. A lot of examples, trying to find some evidence. Hey, that I have this approach. Let's just try to carry it out. Maybe solve something smaller. Also talk to other people. Bounce ideas off each other. And then finally, you find something that sticks, implement it, and you got to present it. Probably lots of mathematicians with here. Yeah, and so yeah, to give oral presentations, right? And so, right, so we only have 2 months. Not a whole lot of time to really maybe even cover this entire ground here. But right, each of these 3 components, like I really hope participants. I'm sorry. Let me just back up. So I really hope participants get a flavor of each of these 3 steps. Okay. And honestly, right, like this kind of 3 steps are applicable to any sort of quantitative problem solving, right? Like, so data scientist, company wants you to, I don't know, optimize their tractor repair, use data to optimize that, or some hedge fund wants you to set up retune their portfolio because rates are going up. Anyways, so and yeah, so on the projects I'll talk about, right? So each of these 3 steps will appear with some different weighting, right? So some of them are like a lot about background material, I first got the proposals, it was like, someone was like, oh, we're just gonna learn this. I'm like, we're a university, we don't pay people to learn things, right? So, right, so, you know, like, tell me what your students are gonna do. Examples, smaller problems, and then I'll think about what they might write about, right? Like, you just not only do background material, you're just gonna like, you know, copy a textbook, like, what are you gonna do, right? So, so I really want participants to experience all of this. And you know, again, it's only 2 months, so some of these projects you might be able to actually tackle the problems, some of them maybe not. But again, background material, getting examples, writing things up, your findings up. And so 2 months is not a lot of time. What do you have to do? So there's basically 2 things you got to deliver here. A 10-page final paper with the group, you know, written up with LaTeX here. And want it to be good. And also a 45-minute final presentation. So, you know, a big skill we want students, you know, again, that 3rd step there, right? So, you know, actually present your work. So, to a technical audience, you know, so you won't be giving a TED talk, but a technical audience, but I want people to do a good job at this. And then I think maybe it'll be like a 20-minute preliminary presentation halfway through. So, and we hope our grad mentors will play an active role. Yeah, so they're the one planning this whole roadmap. They'll provide background material for you to look at even before the program, setting up your overall plan. And again, we want you to keep moving. So a lot of times when you're solving stuff, you get stuck. Hopefully they'll help you get unstuck. Like you don't have that much time. And also coach you on presentations and so you want to always be moving, you know, so just like Bruce Lee, you know, water. And also, right, the various stages of these 2 months, right? Like if you're learning material, you'll probably be doing your daily routine will be very different than if you're computing or coding or if you're writing. So hopefully Anadil will be able to keep you in the right form and moving the whole time. So.
How many mentors do we have so far?
3, maybe up to 5. Okay, so that's basically everything I have to say about logistics. That's about the possible projects. Any questions so far? There's Q&A, yeah.
So you mentioned the possibility of being in person is up to each individual group as to whether they want to try to how they want to collaborate.
Yeah, we're gonna set it up so things can be done all remotely. Yeah, I mean, it's probably up to your mentor. Not really up to you. Yeah. Any other questions?
Will you go over the different project ideas you have right now?
Yeah, so that's coming up. Yeah. Okay, so yeah, so far here's projects we have under consideration here. Some of them are approved. So the first 3 I'm going to list have been approved. One's on graph matroids, Morita theorems, more of an algebra project. Anadil's gonna has something on our regularization, renormalization, and QFT. Okay, so that's minded. So I'd say if you're into like stochastic stuff, I mean, something like QFT is weird, leads with everything. So yeah, and also a project on not polynomials, and this is a graph theory 1 k-neighbor bootstrap collation. So I'll be talking about the first 2, and I'll just like, I could write. We're hoping to have everything approved before this and give people mentors time to prepare presentations, but things are still kind of halfway. So this is just, I'm going to talk about the first 2 because I was like, I could randomly write up slides. These were 3 topics. I learned about enough stuff in a decade. Okay, so graph matrix. So this is more about this is something related to graph theory, but matroids. This is a definition that's I don't know. It might seem really random. So I start with finite set X. A matroid structure on X with ground M with ground set X is it's just a collection of subsets here, satisfying some properties. And these at first hand look very, very random. First off, empty sets kind of. Okay. And then if you have two sets, if you have a set in M and then a subset of it, A prime, then A prime is also there. Okay, so downward closure. And this is the really random one. So if you have two sets in M and one is bigger than the other, then you could always take something from A, the bigger one, attach it to B, and still be in M. Okay, augmentation. So what is this trying to do? Okay, so the main, sorry, before I say that, and then let's say two are equivalent if there's a bijection between the ground sets. That also, right, so if you have map between two sets and also take subsets to subsets, and then hopefully you want this to also be a bijection at least on the matrix. Okay. Yeah.
For property 3 here,
Yeah.
are we just saying there has to be one element per situation like this?
Yeah, just there is one. Yeah. Mhm. So what are these? What is this thing, and why does it matter? Was it some examples here? So the main example that you might run into if you're learning about matroids is take X to be the columns of some matrix. Given some matrix, take X to be its columns, and then just have M be the collection of linearly independent subsets of its columns. Okay, so I throw in the empty set, yes. Yeah, so let's look at these three conditions here. Right, so learn about linear independence, right? You can always go smaller. That's B. That's number 2. And then this augmentation is a little weird, but if you think about this, yeah, I don't know. Just think about it.
It ends up guaranteeing that the set starting with B eventually becomes the same size as A.
Yeah, it's like a dimension thing, exactly. Mhm. And so this is my matrix X, or my matrix and X is its columns here. Right, you have some operations to maybe try to read off this matrix structure, right? When you go to reduced row echelon form, you get something that's a bit easier to read, right? Okay, look, so for example, like these two subsets are the subset of these two columns. This is in my matroid. Sorry. So these row operations that you turn this matroid, the matroid, turn this matrix into this matrix, and it actually respects the matrix structure. So like looking at this mess here, you compare it to this matrix, and you realize, okay, look, for example, columns 1, 3, and 4, they are not linearly independent. Harder to read from here, but from here you can see these two. That was a little bit chunky. Okay, so for these examples in the linear algebra, you do have these operations that maybe make things easier to read. Okay, so this project is primarily about graphs. So what I mean by graph, just vertices and edges, is a very lazy graph. And some people in different contexts, maybe you would augment this, maybe you want some directions. This is meant to like model some network connection here. And so in a cycle, it's just a sequence of edges that starts at a vertex here. Okay, so here I only have the cycle by that triangle. And so the cycle matroid of a graph, you just take the ground set to be the edges. And then and you kind of treat having a cycle like it's being linearly dependent. So the subsets in M are the subsets of edges that don't contain any cycles. And so now think what's going on here, right? So like reading off this matrix structure on a matrix, right? You can do row operations. You've done this for weeks in a linear algebra class. It's doable. And then now this is something more qualitative on a picture, and it's kind of well that these two things maybe you can treat similarly. Right? Yeah, so just like you have all these row operations that give you start off with that matrix and you make it much simpler, preserving that matrix structure. You know, what are some operations that you'll need these inputs here? That's a question I think it's probably answered. But then also like you could define many other kinds of matrix associated graphs and ask similar questions. What are like the row operations for these graphs, right? So that's kind of what this project is explored here. And yeah, the matroids, you could Google it, show up, and like anything to do with graphs probably show up, you know, if you're in computer science and data and stuff. It's overall a very active field of research, applied and theoretical. Yeah, there's this guy, Jun He. Great. Yeah, he was look at the story. I mean, it's just like he was a physics major in undergrad, and then he felt like he wasn't good at math, so he was going to be like a science journalist. This is in South Korea, and so the Japanese mathematician Hironaka was giving like a year-long course at his university, and so he decided to sit in just to like maybe he'll be like maybe write an article about him or something, and then he just kind of sat there, and then this course just became super abstract. Everyone was leaving. He was just kind of up there. Now he's proving big theorems on matrix. So yeah, it's cool to be in a field that's moving forward for young people. All right, so that's about matrix. Any questions? Yeah.
So you mentioned that this approach is not a question that isn't still open.
Oh no, this still has some. I mean, probably that question I listed probably not letting you define.
So are there like
other matrix
set questions or ideas that the project would approach?
Yes, there are. Yeah.
So like the example, so like for a cyclomatroid, it's like, would you use like it's like of a matrix representation of a graph as like for the matroid?
Yeah. So
So like just ones and zeros then in the graph.
yeah, that's in its matrix. Yeah. So kind of the so yeah, this is actually quite a. The cyclomatroid is actually the incidence of a matrix in this case. Yeah. So this will probably involve a lot of linear algebra. I don't know. I'm not that organized. Yeah. Or I'm not the mentor. Any other questions? Matroid theory is just a lot of stories. There's this Junho story. There's this congressman in Illinois, Daniel Biss. He proved some like big result in like matroid theory, and then it got retracted. But he went on to become a politician.
Not always like mine.
Yeah. All right. So I'm trying to talk about it's more related to abstract algebra. What are about rings in here? Rings out. Yeah. So well, it was built in. So yeah, a set basically you can add and multiply. I'm not assuming that the multiplication is commutative. But you're setting that there's some distributivity property here. I guess there's also one for the right multiplication. All right, and some examples. Okay, yeah, integers mod something, real numbers. Set of n by n matrices, and I'm not gonna cut off here. Real values through variable functions. You can add and multiply them. Yeah.
Are we talking specifically rings with a unit or not?
They don't have to be unital. Yeah. Well, I mean, oh no, actually, probably for this, you want to, yeah, let's say what unit, sorry. So one thing maybe less encountered in undergrad, is I have rings, that's all about modules. So an R module, my ring is R module M is a set equipped with its own addition operation, and then a way to multiply elements of R with elements of M. And the thing to kind of think about is, well, you have the field R, real numbers, and real modules for the real numbers. These are just vector spaces. So vectors, you can add vectors, you can scale and multiply. So think about the multiplication by elements in the ring R as your analog of scalar multiplication. That's kind of what's going on here. Things get a little bit fancier. Right, so you could actually think about this in the integers mod n. You can multiply with any other integer. Right? There's a factor. It's class mod n. The more geometric, well, 3D vector feels like a multiply with a 3D function, right? It's a module. This is just like, it's like, what are the applications of the thing? This is just like a very, very, this is a definition that shows up in a lot of places. Both in algebra, number theory, geometry. And then you could define a notion of a homomorphism between the two. So you have to respect addition in the module and then multiplication, scalar multiplication. You think about what linear transformations are, these are, so the homomorphism is kind of the analogs of like linear transformations. And then if you consider our modules together with these homomorphisms between them, form something that's called a category. And so yeah, part of this project is kind of picking up the algebraic background, basically category theory. Itself is a very broad and deep field. And so yeah, so prime example here again. So when R is the real numbers are, R modules there's vector spaces, and then these homomorphisms just end up being transformations. So what did you learn in your algebra class? Just this category of R modules. R is the real numbers. And okay, what are some features of this category? Well, you could assign a notion of dimension, and basically, by this whole thing, I'll pick a basis. For this, you have that dimension. Sorry, let me. If you're basically any two vector spaces with the same dimension, you can kind of treat any vector space of like dimension 3, you can just treat as R3, basically. And then you can handle linear transformations between finite dimensional vector spaces just using matrices. You pick a basis, you can write down a matrix. Right, so I'm just saying this category, right? You've seen it before, and you have some tools for working with this. Maybe it's something to note is that any two non-zero vector spaces, there are a lot of matrices. Right? Okay, other examples here. So if I take two distinct primes P and Q, okay, I didn't define what a module homomorphism is, but think about maps between Z mod P to Z mod Q that respect multiplication here. Actually, no non-zero maps. Right? So in Z mod P multiplying by P would be 0, and then that would have to be sent to multiplying by P. Yeah, that's just be the 0. Very distinct primes. So as opposed to real numbers here, this category of Z modules is there's not a lot of maps between some things. So just to point out some features. So two rings are called Morita equivalent if they have similar categories of modules. Yeah.
By similar.
And being very big. Yeah. So, yeah. That's what you have to learn. Yeah, no, because categories are very big. So to say like there's a bijection between the two, it's a little bit asking for too much. Yeah, and so kind of the question, and this is not, well, I don't know, it's open in a very large sense here, but this is, so I kind of, I'm trying to find properties that will detect Morita equivalence. So like if these two things aren't if these two rings aren't similar in this way, then there's no chance the categories of modules are similar. Yeah, so this is kind of a weird, it's gonna get a little weird, right? So actually R and the ring of n by n matrices are Morita equivalent. So it's a little surprising answers here. Right? One ring seems way bigger. They're both infinite, right? So one seems way bigger than the other. But these modules are still, module categories are still similar behavior. And it kind of gives a different way of looking at rings, right? So maybe some rings have big categories of modules, some rings have little ones. So there's a lot of abstract algebra here for people that are nerds like that. I mean, that was me undergrad. So yeah, any questions?
What do you like, I guess, what would be good prereqs to have for like, for this project, I guess? Like
Yeah, I
classes?
mean, I think, yeah, I say abstract algebra is a very, so you all have like there's a group theory course and they are rings separated from that.
Yeah, because
Rings are a separate course.
Okay, yeah. So like rings and fields would be like a great prereq with that. The category theory stuff, I think would be on the mentor to help you pick it up. Yeah, I think that the best would be.
Because I know that we also offer community developer course.
Undergrad?
Yes.
Oh yeah, that would be lovely. Yeah.
So either of those would be, so basically any way to introduce a student to rings.
Yeah, basically, yeah. You learn about modules and algebra?
Should I get those, is Josue on the?
Yes,
No, he's not in right now, but
I know they're not covered in our rings and fields course. It's not covered, the modules aren't discussed, but they might be in commutative.
Yeah, not my field. Yeah, if you like rings and fields, I mean, I think this would be a great follow-up. And modules are very important. Seems like a weird word. It's just like a part of the language. So, yeah, it's just next step. And categories. All right, so this is the one. Just kind of pump this one out in the last hour. Normalization of QFT. So I'm kind of hopefully. Actually, I even hate saying that I'm not qualified because like every talk involving physics, you're like, I don't know any physics. I literally don't know. I literally don't know any physics. Okay, so I didn't take a physics class in undergrad. Okay, so general goal of physics. Okay, right? You start somewhere and then tell me where it's going, right? Predict the future. If college majors are like in Hogwarts, then I say physics should be divination.
I believe that.
So I kind of view this as pushing time forward, right? All right. So main example, you got the heat equation. You solved this a bunch of times in differential equations course. Did these? Yeah, DPQ, and then do you have a?
Yes, Fourier series and PDEs.
Okay, but you cover this in the DPQ?
Yes, the heat equation is covered in our interdifferential equation.
Yeah.
Yeah, so right, when you get to this part, you're always doing the same thing, right? Those are set up. Okay, so you have an initial heat distribution of heat on some or of like 2 pi for some reason. And then you want to find, using this model, right? You want to find, this kind of gives you a rule how it changes over time and throughout the future distribution. All right, so how do you do this? Okay, so yeah, here's your executive summary, right? So you compute the Fourier series of your initial distribution. How do you do this? You compute all these integrals, right? So this is the main nightmare. you know, all these coefficients, and then, well, how do you go forward in time? Hey, look, I did it. That's going forward in time. Right. Right, and so you go back to the heat equation, the second derivative equals the derivative with respect to x equals the derivative with respect to t. And this it literally comes up to satisfy that. Right? So, boom, that's moving time forward. All right, and you kind of you actually create it and just write it. Like, what do you do here? Well, you're multiplying, you know, different weights on this e, right? Depending on what your series are, but you can write it uniformly as well. You're just literally picking up the if you take the derivative twice here, you get it negative n squared. So you just write it like this. You push time forward in the heat equation and in general. So yeah, to summarize, right, pushing time forward on this heat equation, rewrite it with this operator notation here. You just apply it. You just do that. Yeah.
So they don't have to take the E's anymore, huh?
Yeah. No. This is incredibly. This is either what you do in every situation or what you would like to do.
Yeah, no, this is the exact kind of difficulty I want in all of my differential equations.
Yeah. So this is really handy. So in quantum field theory, like you replace the second derivative of x, and even the things, so instead of just a function, it's a single variable function, something far more complicated. But the same idea. But you wanna see how things go forward in time. And
Is this H for the Hamiltonian?
yeah, H is the Hamiltonian. Yeah.
Yeah, I'm currently in QM.
Perfect. You are the super for this project.
More suited than I am. Yeah. So this is so you literally just want to do this. Okay. So it's pushing time forward. Yeah, we know what this looks like. So this is the part. It's like, okay, it's really nothing new. But right, and then when H gets complicated, you use the following argument, right? So you argue, okay, actually, oh sorry, this is value format, right? Okay, let's say I argue that I actually know how to do this for like small values of t. Okay, so I know how to push time forward little steps. And then so you break your interval into pieces, and then you're like, well, if they're small enough, you claim that you got to do it on small steps, so just push it forward that many times, and then you take it to infinity. So this is what's called the path integral, basically, and yeah, so getting a handle of this thing is very roughly the idea of the path integral. Just break your time up into pieces by step. Take infinitely many steps, right? Often it just spits out nonsense, so you have to clean it up, right? So what's an example of nonsense? Like Zeno's paradox, right? Take infinitely many steps and nonsense. You can't be faster than Achilles. Okay, so yeah, and then there's also kind of a vague sense. This is kind of really stochastic, something like what they want to say. It's probably some feedback here, so like alignment. Okay, let me just leave that vaguely. Yeah, so some of the stuff on like renormalization here does also show up in stochastics. Okay, so that's really all I have to say. Yeah. Yeah. Any questions? Let's take it. What background would you recommend for the QFT?
What I recommend, so it'd be really good if you know quantum mechanics, classical mechanics, to the extent that you're familiar with variational methods and Weather-Lagrange equations. Linear algebra is a must. Fourier analysis, in the sense like knowing Fourier transforms and Fourier series. What else? Group theory. Complex analysis up to conjugate integration. Have you heard of this? Okay, perfect.
Coincidentally, we're both also in a class that's covering Fourier and complex integration.
So what we will do is, well, he did a very good job in like explaining the like what we're doing at the level of philosophy. We will see how like we we will first of all see the difference between quantum field theory and quantum mechanics. And then we will develop path integrals using inspiration from quantum mechanics. We will develop path integrals for quantum field theory, which are very different beasts. And we will realize, so then we will pull out propagators from that path integral, which correspond to essentially Feynman diagrams. So we will also develop this back and forth between our integrals and Feynman diagrams. So you will learn essentially Feynman calculus, the Feynman diagrammatic calculus. And then we will realize that the integrals that we have are, they should give you physically sensible results in the sense that they should be finite, but they end up being infinite. So we will go back and fix them, and that fixing process is renormalization. And a consequence of that process is that our coupling constants in the theory change. And then we will spend some time studying that. So yeah, there are many things that we will do. And depending on how slow or fast we go, we will start off with a very basic type of field theory. Your job would be to learn how to do renormalization on that basic theory and then extend it to like a very decent case and see how that goes. And depending on how fast we go, we can make it more sophisticated. We do not need to restrict ourselves to bosonic fields, for example. We can go to fermionic fields, we can go to gauge fields, and maybe statistical field theory. Interestingly, so renormalization is statistical field theory is like slightly easier than full QFT. I know less about that, so I will have to spend some time learning statistical field theory. But yeah, that is stochastic.
My first question is about the stochastic element specifically. As someone who hasn't really done much with advanced statistics, stochastics, that's not the focus we're approaching this mathematically, right?
That's it.
Okay.
And then you don't need advanced statistics or probability.
My other question is, where does this lie in current QFT research? Or
This is like basic stuff that every mathematical physicist should ideally know. But so far the final thing that I have in mind, we can go beyond that. The final thing that I have in mind is we will reproduce a result that was published in 2015. Part of that result. So in that sense, fairly recent.
I have a question in sort of the same vein. I have some of the quantum modern physics, auditability algorithm. I don't have all of those, but someone mentioned that before each of the REU start, we're going to get some like sort of pre-assigned reading that'll help us catch us up.
Yeah.
Your research.
Yeah. Depending on interest, I will certainly assign some readings so you guys can catch up before we start the project. And always come back and ask me like, what does this mean? Where does this go?
So I would say, the fields of math that I work in are actually very adjacent to mathematical physics. And my great regret in college is that I never learned any physics. And I tried to do this and like learn QFT in like grad school. I'm like, I can't do this anymore. I'm like, I'm in my mid-20s. Yeah, I don't know. I think,
So yeah,
someone's gonna give you a
one thing
curated
that I
book
would like
to
to say is the sooner you get into QFT, the better it is if you wish to do mathematical physics that would rely on QFT in the future. Because it gets increasingly painful because the way physicists approach this subject is fundamentally painful for It's lacks in rigor. It's we will also do it exactly the way they approach the subject. It would be the level of rigor would not be mathematical physics, it would be theoretical physics. But if you do it now, it will be less painful later. Provided this is something you wish to do in the future.
Actually, I have probably burned so many hours.
That was grad school. That was just all of grad school.
Yeah, that's just is grad school.
Yeah, well, yeah. Depending on who your advisor is, it can be.
I mean, I guess this is like, so feel free to ask. I think there's 4 of us, yeah.
How did you come up with these problems?
Or like find them, think they're appropriate like a 2-month thing.
That's a good question. I mean, the mentors get paid, right? So yeah, I mean, like, if on my
Find something. that you would be able to do.
If it feels me personally, like what probably I would do. I mean, there's like so I don't know physics. I also don't know how to code anything. So for me, but this has nothing really to do with any of the fun. Like I'm just talking about. I mean, I would like be great if some undergrad could just code some stuff for me. So I'd be like, okay, well, what do you need to know?
I would also like to say something once you're done. That's it. So your question was, how do we come up with these problems, right? So what I did essentially was look at something that's an active area of research and reduce it down to its lowest level. And that's how you come up with problems. Lowest possible level. And then you start from there and then you go as far as students can go.
The QFT, that's the lowest level.
That's the lowest level. Do you want something that's an active area of research? Want something that's like done 70 years ago?
Absolutely.
So with the physics project, we got an idea of where it's placed relative to current research. Where do the other ones lie? Like you said that matroid theory is very active, and the other one that there are still people trying to compare and find what these detectors are.
Yeah. So the matroid one, again, so it's fortunate we don't have the actual mentor here. I think my understanding does have like open problems online. Yeah, and then again, that's a field that's very CS adjacent, so there's a lot of coding stuff that. The Morita theory one, that's mainly going to be like a learning project. To be honest, there comes no problems. On the other hand, you're going to be, like I said, if you did group things and fields, like this is literally the next step. I don't know how you live in a world where you apply group things and fields and you don't learn modules and categories. So if you just like that stuff, that's the next step.
You got the slide with all the projects.
Might take a while.
Do you have a if you wanted to learn more about some of learn more about some of these projects, you have the is there any contact info for the mentors behind some of these projects? Or is it still in draft, still in
Yeah, it's still kind of a draft. I mean, I think once we approve them, I think I'm gonna ask the mentors if they literally just have like a PDF, to force them to write things up. And so my say on it, they'll quote my post this. Yeah, so you post a proposal. Might not be cool. But short answer is hopefully yes.
Yeah. The knot polynomials one, would that be like calculating polynomials for different knots that are like Kant polynomials, like Jacobi polynomials, or would it be trying to find new polynomials? Or
No, it'll be studying existing ones, and this would also be a bit more of a learning project, what I understand. So yeah, we're computing, mainly focused on what's called the Jones polynomial, and then it's just a thing where you just draw pictures and you just kind of compute off it, but there's actually a lot of deep math and physics behind it, so more learning that kind of stuff. Might take a while to get to the cutting edge of that. Other questions? Yes.
When though should we expect the decisions to be released?
At least soon. So I'm okay. Well, the deadline's next week.
And that is a rolling deadline, yes.
Well, the rolling deadline is like going right now.
Right.
Yeah. So that's like the deadline.
Yeah, so like it's been rolling this time.
Yeah. I think, and honestly, I think it would probably take more than a week to get things totally finalized. So,
The week from the 18th.
yeah. So originally we thought we'd get the mentor things all finalized before this, but it's just gonna take longer. So I don't know, maybe 2 weeks after next week.
So their final deadline for application is before the project's fully finalized.
Hopefully everything's finalized by Monday. I don't know. Yeah. Things are just taking longer than. And if you apply, you have to submit a personal statement, right? So if you're like, I'm really interested in like this one project that was explicitly listed and it's not happening anymore, I mean, we'll note that, right? So feel free to mention once you're just,
If we already sent an application
yeah.
and we have interest in a specific project, how would it take us to approach that?
Oh,
Just email.
yeah, you just email us, email, yes, like the, add these little edits, or maybe the easiest thing, you just just send us like a new personal statement, and then we'll just replace it on the drive file. Other questions?
Not necessarily a question, but more of a comment for you all. This is definitely something you should consider doing, or at least applying to. It's a great program. Obviously, it's basically an REU, all but in name technically, but I mean, you are actually doing stuff for the full 2 months. And yeah, it's your working groups. It's a really good time. You're gonna learn something, even if you don't like actively contribute anything new. You're definitely still going to learn a lot. And there's a lot of sort of great opportunities to connect with other people, the other groups, listening to presentations, going through the final paper writing process together, that sort of thing. So certainly if you have any questions about just generally just sort of questions that you want to hear from a viewpoint of someone who's done it before, feel free to reach out to me at any point and ask.
And Nick's project last year had a paper that came out. Well, it's on the archive.
It's on the archive, yeah.
But, yeah, so it turned out, I think, very well for their group.
You wanna plug it?
Plug your paper on archive. I can put the link on the next card. So yeah, I can send it out later, but it wasn't anything interesting. It was more of a the TLDR is basically we were looking at, say you have some number, these things called configurations in geometry, where it's basically you're looking at you sort of have a set number of sort of intersections that you've defined. So say if we have an N3 configuration, really what that means is that each point has 3 lines going through it, and each line has 3 points on it. And then you can sort of vary the number of lines and points overall. So actually, if any of you went on the Museum of Science trip last week, we did see some examples of configurations in the Mathematica exhibit. But that wonderful. Yeah, exactly. Where we spent 45 minutes talking about it. Yeah. But yeah, so there's obviously that it's more geometry, but then you can sort of get into more combinatorics, number theory. Obviously, there's group theory involved too, and so you can do a lot of just simulation and modeling, that sort of thing. So the paper was more focused on some Python work that we did. But yeah, I can definitely send it out in the Discord if people are interested in looking at an example project.
And there's all of the projects from the last
That's true, yeah.
4 years that this program has been running on the REU website, so you can see sort of what the final paper kind of looks like and what's expected.
The presentations themselves, right, are not posted?
No, I don't think the presentations are, but the papers are.
Yeah. So I guess that kind of wraps up what we had today. Thank you both for coming and sort of talking about this. Really appreciate it. So again, highly recommend applying if you have not already. Yeah, feel free to reach out. And then I guess as part of and when you post the recording of this, would you mind if I sort of send out your email as well, just so that people have it?
Yeah, go for it.
Okay. So their contact info will be as part of the email. So if you have specific questions, feel free to reach out to them. But like I said, that's pretty much it for today. There's still plenty of pizza, and it kind of needs to be gone before people leave. So grab a couple of slices, please. Yeah, I mean, obviously we have the room for another little while, so feel free to stick around. And please make sure to scan that QR code. I know some of you have not yet. So please do that before you leave. It is an attendance form. Sort of a running joke we have that, you know, about half the people scan it each time. But helps it.
The department's never gonna pay for it.
Right, well, it's like, when I give them like the
They're
number,
like,
the
this is
count.
the bare minimum, it's actually 1.5.
Well, I actually have to like explicitly say, add 5 to all accounts for this meeting.
They were all very much.
Oh, it's good paying. Well, yeah, I mean, so are you following along with my Yeah, so I'm doing office hours 5 to 6 Tuesdays. Yeah, it's on Zoom, but I